calculate one simple example of the Taylor-Wells, of the deformation ring. Can I turn it off? Anyways, so last time we calculated a simple example of deformation ring. So I'm going to do another one today. I think this is a very important calculation. Maybe I'll call it Taylor-Wells deformation. So, okay, so find the extension of QP, and P is different from the coefficient L. Oh, thank you. I'll take the same setup as before. I'll consider a row bar a representation, and I want to take it to be an unramified representation. So small k, capital K is the residue field of K. So it's an unramified representation. And to characterize it, basically I just need to tell you where the geometric forbiddeness goes. So let's say it goes to alpha bar and beta bar. For alpha bar, beta bar in F. And for our later discussion, to make the ring more explicit, I'll just basically fix two lifts. I mean, this is in GL2F, so it's alpha bar and beta bar in F cross, so I can lift them to units. So I'll make the following assumption. I want to assume that alpha bar is not equal to beta bar times Q plus minus 1. Maybe I should say this about the number of residue field of my field is Q. Okay? This modulo. If alpha bar is congruent to beta bar times Q plus, Q times beta times Q or beta divided by Q, then the deformation ring will be more complicated. I'll just do this relatively simpler one. Okay. As in last time, any lift, let me call it rho, from GK to say GL2A, where A is in the category of complete Noetherian local ring. Gives me complete Noetherian O algebra, right? Whenever you have a lift of row bar, this will always factor through the quotient by the wild inertia, right? Because wild inertia is pro P, and this guy, I mean, except for on the residual part, the part 1 plus var. So inside of here you have 1 plus. Remember that you have this part. Right, and this is completely pro L. So this pro P group has trivial image in this intersection with this pro L group, and also this pro P group, in some sense, has no image in has trivial image in GL in the residual part. So therefore, it factors through here. And this guy is maybe just write it over here. So this is Z hat 1. Product of Z. Okay? So this factors through here. And I basically need to understand how Frobenius acts and how tau acts. Right? So if I want to understand deformation ring, I would just have to sort of understand how Frobenius and tau act on how they can lift. So now I'm going to claim the following. Suppose we're in such a situation, we have such a lift. My claim is I can find eigen vectors of phi. I have two eigenvectors. One of them is, well, I mean, maybe before that, this modulo pi, I have two eigenvectors, 1, 0, and 0, 1, right? They have eigenvector for phi. they have eigenvalues of alpha bar and beta bar. So now, when I lift them, I want to say that, okay, I can not only lift this representation, I also at the same time lift the eigenvalue and eigenvectors. So the first eigenvector, I want to set it to be 1x for, I'll have 4 variables, x, y, s, r, in the maximal ideal. Whenever, when we say eigenvector, it's always up to a scalar. So I can make the first entry 1. The other entry is x. This with eigenvalue. Well, originally it was alpha bar, so I lifted to something. So this will be alpha plus s. In the same way, the other eigenvector originally was 0, 1. It will lift to some y. And then this is beta plus t for t. Okay? So I claim this. I can lift this, the original eigenvector of phi, which is 1, modulo maximum ideal is because 1, 0 eigenvalue is alpha bar. And this is 0, 1 eigenvalue is beta bar. It was just what the matrix was. So let's prove this. Somehow, basically, essentially, this is some sort of Hensel lemma. Hensel lemma type argument. Let's maybe just do the first one. Okay. Lifting the other eigenvalue and eigenvectors are the same. So say we have computed x and s modulo the maximal ideal to the nth power. Now we'll decide determine the modulo of maximal ideal to the n plus first power. Right. So this is some sort of Hensel lemma type of argument. So what do I need to do? Well, back to freshman year. So let's do this. Oh, I have the A being the same as this A. Let me just use this A. There's no way to confuse this A with this ring A. Okay. So this is what is this? This is rho phi. Okay. Rho phi lifts rho bar. So therefore, it must look like this, where A, B, C, D are in maximal ideal of A. That looks very bad. But anyways, okay. So this is my rho phi. Okay. We say, okay, we want an eigenvector, which looks like so. Right? So let's just solve this by brute force. Okay. So we want this. So we have computed x and s. Well, so this A, B, C, D are somehow known well all the way, but we want to find the x and s in this. Okay, what do I need? Okay, this times this equals alpha plus s times 1. So I need 2 equations. First, I want alpha plus a plus bx equals to alpha plus s. Yes? Right? This, this times this equals alpha plus s times 1. Okay, now I kill the a, alpha. So you see that somehow s, so once you know x, basically s will be determined. And in fact, maybe I should say, knowing x modulo maximal ideal to the nth power gives s modulo the next power. That's because somehow the only thing that depends on x is this b times x. This b already itself is in the maximal ideal. If you know x modulo maximal ideal to the nth power, it will tell you what s have to take modulo the next power. right? So A is known all the way, B is known all the way. So S must be equal to that. And so on. We want to solve this, right? I mean, we know x modulo maximum ideal to the nth power. But this B, the coefficient on x is in the maximum ideal, then of course the ambiguity here is modulo n plus first power. That's the first thing. And once you have this, you do the second one. You do the second one, then you have what? C plus beta plus D x. That is equal to, on the right hand side, alpha plus s times x. So maybe I'll write x times what alpha plus s is. Right, so I plug this in. So this is alpha plus a plus bx. So the left hand side is c plus p beta plus d times x, and the right hand side is alpha plus s times x. But alpha plus x by the first equality equals to alpha plus a plus bx. So this is a typical Hessel lemma type of argument. So what do I want? Let me move on the other side. Move to the other side. Let's simplify that a little. Okay, what do I get? Let me put the x on one side. So I have beta plus d minus alpha minus a times x. That's equal to minus c, negative c plus bx squared. I just move things around. So basically, the linear term I move to the left, and all other terms to the right. Okay, remember that I know x modulo maximum ideal to the nth power. So here's the upshot. Okay. Oh, I apologize. Looks like I need another assumption. Sorry, earlier. I apologize. I also need to assume that alpha bar is not equal to beta bar in that, or rather I need alpha bar modulo beta bar to be not in 1 or plus minus. Q or Q inverse. Sorry, I apologize for that. I missed the condition here. Okay. So with that condition in place, alpha and beta modulo bar pi is not 0. So if you look at this one, so this is not 0 modulo maximal ideal of A. So whatever this thing is, so it's a unit. Now now this is determined. And now I can use some, how Hessel lemma is proved, right? Once you know x modulo maximum ideal to the nth power, then this number is determined modulo n plus first power. This bx is determined modulo the next power. So then I basically just set, basically using some sort of Newton iteration. So at x to be sort of this beta inverse times minus c plus b x squared. When I say x squared, I really mean x mod maximum ideal A to the n squared altogether modulo. And that determines this x modulo the maximum ideal to the next power. And you can iterate this step. And therefore, when you take the limit, you get this sort of A, B, C, D. Excuse me, you get the solutions for x and s, the eigenvectors. This is standard Hensel lemma argument. Maybe not in a spelled out way, but okay. So we found these eigenvectors and eigenvalues for this lifts of representations. So now, once we have them, we know that by linear algebra, this rho phi must be equal to 1y xy. Right? When you know eigenvalue and eigenvectors, and also the eigenvector form a basis, then you can rewrite the matrix as so. Now, I want to understand what rho tau could be. Well, because I've already written phi in this way, so I might as well just write tau in the same way. Or maybe I should also say that, the determinant of this matrix is 1 minus xy. And xy's are both in maximum ideal. So 1 minus xy is a unit. Right? So therefore, this matrix is invertible. Although I don't care what really it looks like. So I want to show, in some sense, I want to show this tau in the middle. Somehow phi and tau have some sort of commutativity relations. So I would somehow guess that somehow it should be also diagonal. Let's maybe do that. What do I do? What should I do? Modulo maximum ideal, this tau is just identity matrix. So maybe I'll write sort of formulate this as sort of 1 plus some p and some q. Okay? Where my p is p11, p22, and my q is anti-diagonal. Okay? And my goal is to show that the q is trivial, and therefore I have a diagonal matrix as so. Well, let's see. This is, once again, another sort of Hensel lemma type argument. Oh, remember there was a faster proof for this Q to be trivial. Slightly faster, just a tiny bit faster, but I couldn't find the proof. So let me just maybe give the naive proof here. Right. Okay. So now we know that phi inverse tau phi equals to tau to the q's power. Right. The Frobenius acting on the tame part is given by the cyclotomic character. So if this is conjugated by the tau by the inverse of Frobenius, or inverse of geometric Frobenius, so it's arithmetic Frobenius, we're raising tau to the q's power. So plugging in what this rho of that is, I would get, let's see, what do I get? I get the left-hand side. We all know conjugation. If you take inverse, use conjugation. If you multiply all these conjugations together, it will be somehow multiplying the inner part of the conjugations together. So I would just get R. Maybe let me just write the outer part as well. You know this will kind of go away. Did I write 1? When I write 1, I mean to say I2 maybe. It's sort of the same thing. maybe I have to put this thing here. That's the left-hand side, and the right-hand side is times tau to the q's power. So this is 1 plus. Right? So I multiply them out, these matrices. So kill the part that's obvious get killed. So this conjugation part get killed, because it doesn't really matter. I mean, whatever you call it, you can compute this, you call it under any basis, basically. I can compute it under the basis at 1x and y at 1. Okay, so now we're left with this. So I claim that, so I claim that q is just 0. Why is that? So suppose, so proof of that. Suppose that we have proved, again by induction, that Q is in maximal ideal to the nth power. I mean, we have two entries, so it belongs to maximal ideal to the nth power. You have two variables, so that. Okay. Namely, what I mean by that is both Q12 and Q21 are in that. And what do I have by looking at that? So let's see. Expand it out. Hang in there for a second. So what do I get? I get sort of identity matrix plus. So this is sort of alpha plus S inverse. Ouch. Beta plus T inverse of this P of same thing, and plus this thing inverse Q. Same thing, right? That's the left-hand side. Right-hand side, let's sort of expand it. I mean, this is, again, sort of some Hensel lemma type of argument. Right-hand side, I want to write it as sort of, let's see, how do I want to write? I want to write this plus P to the Q's power plus use binomial expansion. Q minus 1 times right, I should plus Q here, times Q, and the plus choose Q, so maybe half of Q. Minus 2 Q squared plus right? So I expanded out the Q's power on the right-hand side as well. So now we're in such a situation. Good. So now I want to compare. I want to look at these two corners. So the anti-diagonal part of this. Let's see which matrix matters that. Somehow. This term doesn't have the anti-diagonal thingy, so I can ignore this part. Right? I don't have to look at it because it's all diagonal. P is diagonal, Q is anti-diagonal. So this part I have to look at. I'll do that in a bit. Okay? And this bit is completely diagonal, so it remains diagonal. This one does have an anti-diagonal part, which is coming from Q. So let's box that. And this part. Okay, I guess it doesn't have, but anyways. But my point is that I don't want to look at this sort of. I want to look at the whole thing modulo maximal ideal to n plus first power, right? So everything after that will have some Q squared and Q cubed and so on and so forth, and all of them are in maximal ideal to n plus first power. So all of these I don't care. The only thing, if I just look at sort of the anti-diagonal entries. I just have to look at the two blocked pieces here. Other terms, I don't care. Where's my chalk? Yeah. Okay, so let's actually just compute these two terms very carefully. What they have, what we have. So my Q is Q12 and Q21, right? Now I conjugated my Q by this matrix, so let's write alpha plus S beta plus T and alpha plus S beta plus T. I conjugated it by this. I don't know how fast your matrix multiplication is. If you conjugate it by diagonal matrix, the 1-2 entry, this is conjugated by inverse of this. The 1-2 matrix will be multiplied by, so whatever I have on the left, over here, you have over here. So this will be alpha plus S minus 1, beta plus T minus 1. This is the other way around. Okay, after the conjugation. Whereas, let's compute this guy here. So this guy looks like, what do I have? I have, compute this is nightmare. But hang on a sec. So I have at the end of the day, I just want a modulo maximum ideal to the n plus first power, right? So when I do this over here, the Q is already in the maximum to the nth power already. So whatever that multiply onto Q, I don't have to care that much. I basically just need to look at this guy here, modulo maximum ideal, right? If I have some piece here, like P here, which is in the maximum ideal, times this Q, the product will be in the maximum ideal to n plus first power. So this P doesn't really matter if I modulo maximum ideal to the n plus first power. So I don't have to look at the P. So all I get is just Q times Q. So these P's, okay, this P will create something, but this will be in the next layer of the next power of the maximum ideal. In fact, for the same reason, on the left, I'm making things too complicated. Over here, I don't have to write this. I can simply write what I write. I can simply write beta bar over alpha bar, and over here I can just simply multiply with alpha bar over beta bar. Then I can just modulo maximum ideal for this, because anything that's not in the maximum ideal multiplied with Q is already in the maximum ideal to the n plus first power. So now things becomes extremely simple. Now what do I see? Okay, let's maybe do one of the equalities. So I have Q12 times beta bar over alpha bar. That's equal to Q times this, right? But luckily I didn't erase that. So this is not, or beta bar is just not Q, because I avoided the Q inverse. So I deduce that Q12 must be 0 modulo maximum ideal to the n plus first power. And for the same reason, the other one gives you same reason. Tells me this is next ideal. And then of course when we take a limit, Q is just 0. The anti-diagonal part is completely 0. So this part uses the fact that this alpha bar and beta bar are not congruent to Q or Q inverse. Okay, so now we're back to this sort of rho tau being So now it's a diagonal matrix. Maybe I'll just write it 1 plus u, 1 plus v. Okay. Oh, sorry. Up to conjugation. Right. Up to conjugation. Right. Up to conjugation is a diagonal matrix. Okay. My tau is this. Maybe I just write down earlier that my phi is the same thing. So alpha plus s, beta plus t. Now I want to. So we use that relation to determine these are 0, but that relation will also at the same time impose something on this 1 plus u and 1 plus v. We'll see. So let's see. Let's do this multiplication again. But this time things are a lot easier. So what's the condition real? I mean, once again, somehow we can ignore all the conjugations because basically we're just computing it with respect to a different basis, right? If we ignore all these conjugations, what do we get? We get that okay, alpha plus s, beta plus s, beta plus t, time inverse times tau, which is 1 plus u, 1 plus v. I think if you're fast, you can just see that this simplifies quickly. This is equal to 1 plus u, 1 plus v to the q's power. Okay? And now everything's diagonal matrix. Everything, all the matrices we see here are diagonal matrices. So therefore this and this will cancel each other. I mean, like these are diagonal, so they commute. So when you commute out, they cancel. And you have a q's power in this one. So what you get is that 1 plus u to the q minus 1 is 0. And 1 plus v to the q minus 1 is 0. Right. You can divide it over. And that's... and when I write this, I really mean this is sort of if and only if. Not just sort of... So this is actually somehow if and only if. And that's the only condition you need to impose on these image of rho and images of taus. So let me sort of quickly summarize our result. And one more thing. So if I write p to the m to be the factor at p for this q minus 1, this will imply, this is actually equivalent to p to the m being, being 1. Sorry. Was that the question? Sorry. Being 1. Of course. So this will be equivalent to this being 1 and this being 1. Basically, the prime to p part, I mean, the prime to p part is, how should I put this? You could solve this by Hensel lemma or something, or like, yes, you are right. Thank you, L. My bad. So L or P, this is kind of a big debate in this field. Like, some people use L as a coefficient, some people use P as a coefficient. I guess sometimes I switch the uses. The people switch uses all the time, so get confused as well. So I apologize for it. So L. Okay, so that's good. So summary. From all these calculations, I conclude the following: that the universal deformation ring is generated by these variables, and with these relations, so 1 plus u L to the m minus 1, and the universal representation is given by this. So, Any questions? Or maybe let me also mention that somehow when you look at this power series here, maybe we can, in the calculation, we can somehow see what each variable represent in some sense. So let's see. So we can see that so x and y correspond to, in some sense, they correspond to the framing of these lifts, because you're choosing the eigenvector to be sort of 1x and y1. In some sense, if you conjugate the representation by this, you can always adjust the universal representation so that the eigenvectors are just 1, 0, and 0, 1. So somehow the x and y are the framing variables in some sense. Or related to the framing, sort of how you actually choose a matrix representation as opposed to a representation, abstract representation up to conjugation. And S and T are precisely the eigenvalue for the Frobenius. And U and V here are precisely the sort of eigenvectors of this time inertia. I mean, of course, if L minus 1 is not divisible by L, the U and V will go away because you just quotient out by U or whatever. So U and V, you don't have U and V. But it's an important thing for Taylor-Wells method to choose those primes P or like Q or P, same thing, so that P minus 1 is divisible by L to the n for a large power of L. So that you do create some sort of very much non-reduced structure here. Think about this. So if you have some, think about what this looks like. So for example, let's just sort of do an example of sort of, think about what this thing looks like. So this, roughly, I mean, and what is this thing here? I just, everybody knows how to compute it, so. So it's some sort of, I mean, this thing belongs to, I guess, at least U comma L to the mth power, right? The idea you quotient out by. Somehow, if you manage in some sense to make m larger and larger, this will become sort of getting closer and closer to just O of power series, or like a ZL in power series in U. In some sense. You're quotient out lesser and lesser sort of ideals. Right. But anyhow, we'll probably talk about this later. So the idea of Taylor-Wells is we're going to choose things like this, where m gets larger and larger. That's the idea, to help with the calculation. Let me just write one more variant, just very simple variant, but. So when in our application, the determinant of rho bar will be the cyclotomic character, and my PM my M will be positive, and it will be larger and larger later on. So therefore, this condition we have over here. Sorry, I missed the 1 here, because Q is now congruent to 1. So this becomes just one condition: alpha bar not equal to beta bar. So assume that alpha bar is not equal to beta bar. But I also know that the determinant is cyclotomic, so therefore, and also I know that alpha bar times beta bar is just, well, it's basically, it's Q inverse. But then Q is congruent to 1, so this is also 1. So these two conditions basically all I want is alpha bar is not equal to plus or minus 1. So that's the thing we need to avoid when talking about this situation. And in the condition that determinant of rho is cyclotomic character. And this will be the situation where we use, actually. And I want to fix. We talked about the modularity lifting with a fixed determinant. So I want to fix the lift chi of determinant rho bar to be Just a cyclotomic character. Then the frame deformation with a fixed determinant is just a few variables short. So you have the xy and only have the s, because s will determine what t is, and also u, which will determine what v is. And therefore, the rho universal of phi is equal to, I shouldn't have erased that. And our determinant is Q inverse, so this will be R. Because the determinant has to be Q inverse. And the rho universal tau will be sort of the same thing. But over here you have 1 plus u and 1 plus u inverse. Okay. Just say one tiny bit thing for me. I'll be done. I want to consider a quotient of this, or rather, if you think of it in terms of spec of these rings, it's going to be a subspace of the original one. So I want to use this to denote the deformation. Ring. One way to see this is when I can view the rho bar as a representation of the residue field. Okay, my rho bar is an unramified representation. I can either view it as a representation of the pay, or view it as a representation of the residual field. If I view it as a representation of the residual field, I can get a deformation ring as before. Then what I see is that this is the quotient of the big deformation ring, and in our explicit coordinates, this is basically mod u minus 1. So basically, if you think about this, if you take the universal deformation ring as a GK representation, you look at the places where it's unramified. So basically, you just want to send this thing to 1. If you want to send this thing to 1, basically you just want u to be 0. And of course, I wrote it wrong here. Modulo u here. Okay. If you have this ring and you further module u, you're going to get the unramified deformation. But I would like to see it slightly differently. As I always somehow, for me, I always like to think of this geometrically. I want to think of this as either. I'm always kind of confused whether I should write spec or spuff. But these are all affine, so I don't think it matters that much. Right, geometrically, this is a closed. Oh, maybe I should use French version. So closed means this. So if you write in France, if you write this means open immersion. This is closed immersion. Geometrically, what we're seeing here, this is it's a closed subspace defined by u equals 0. In other words, somehow this unrarified deformation, or the deformation of the Galois representation of the residue field, is really the deformation as a big Galois group, and then you look at the locus where somehow these inertial elements becomes trivial. So that's determined by the equation u equals 0. Okay. 5 minutes. Any questions about these? These are just concepts at this moment. So maybe let me try to get the start of my next sort of topic, and then we'll have a break very soon. So talk about relative deformation problem. So we have talked about, I guess, general deformation problem. We computed lots of examples of local deformation rings. But for global deformation, it's extremely difficult to compute by hand. So in fact, the way we approach global deformation is to think of it relative to a local deformation. This is somehow, I guess, the modern understanding of what Taylor-Wells method or the modularity lifting method is. So I'll take a number field. So as a finite set of places of F, including those dividing L in infinity. And for global deformation, it's really better to fix a rho bar going to GL and F absolutely irreducible. Did I talk about what absolutely irreducible means? Okay, it means that if you think of the coefficient, if you change the coefficient to GL to algebra closure, it's irreducible. Okay. I mean, sometimes if the coefficient is too small, you may not be able to see the I mean, I get the direct summand that makes it not irreducible may not be defined over F. So you might falsely thought that was irreducible. But absolutely irreducible means that when based on algebra closure, it's irreducible. And also I fix a lift. Of rho bar. And for each V and S, where is it? Excuse me. For each V and S, I write rho bar V to be rho bar restricted to the local Galois group, which is the local Galois representation. And also in the same way, chi V is chi restricted to the local one, which lifts, of course, lifts the determinant rho bar V, because of the global one it lifts. Maybe a caveat is that the global rho bar I assume to be absolutely irreducible. But the local one, when you restrict to the local Galois group, which is a smaller group, so very often actually, it's not, this rho bar V is reducible. Okay, after the break I'll explain, so like the issue here. So globally I want to make the usual sort of unframed deformation, but locally we have to use a frame deformation. So there's a way to kind of reconcile these to make things sort of make sense, I guess. Okay, take a break. So this is a formal group scheme. It goes to groups, sending A to 1 plus matrix A cross over 1 plus maximum. Oh, excuse me, maximum ideal A. Maximum ideal A cross. Okay. So, right. So we use that just to discuss the idea, not to do much. Okay. So we have, let's recall before the break, we have this global representation. We have some local restrictions. So then we have natural transformations of functors from deformation of rho bar to deformation of rho v. Right? So whenever I have a representation, whenever I have a lift of rho bar as a representative of GQ, I can restrict to a lift of representation of GFV. Not GFV, sorry, GF as GFV. Right? I mean the sense of the rho to rho restriction to GF. And for every V. And so if you remember the notation that I use X rho bar to be, let me write this back of so R rho bar. And same for the other one. And then when you have a function as so, it will induce a, I always like to think of this geometrically, a morphism of the corresponding deformation space. Maybe if you're not if you're not very familiar with these languages, let me sort of briefly explain what's happening. So I mean you have a rho universal deformation ring of this rho bar. With coefficients in this global deformation ring. And of course your local Galois group embeds in here. Whenever you have a global universal deformation, you can compose it. You get you get the representation of the local Galois group, which also lifts. So this obviously lifts rho bar V, and then by universal property of its local deformation ring, I can find a map from R rho bar V framed to R rho bar rho, such that this is the same as you take the local universal one and then compose, let me call it phi v. You compose phi v, get to right? And then if you take back, you reverse the arrow, so you get to this one. Just quickly explain where do you get this from. It's just sort of playing with some abstract nonsense, and then you get this. As before, I like to think of this in terms of stacks, because the framing is always somehow, for me, it's always kind of confusing, especially after I introduce the next notation. Let me put a quotation mark. There's a question of whether you can actually take the quotient or not. Nonetheless, let's sort of pretend we can do the quotient. And also, I should also correct some earlier mistakes. When, I mean, it's better not to write spec of something quotient by some formal group. I should just write spef of that quotient by some formal group. But everything is affine, so I mean, it's not that big deal. Okay. Oh, sorry, no frame. But I want to sort of think of this as taking quotient. And then what I really want is basically after taking quotient, there's no frame. We're just talking about representation as abstract representations, no sort of not matrix representations. But I really want to do the following. I want to understand the global representation, the global deformation space, relative to all the local deformation space. And so, as abstract representation. So that's what I really want. However, this comes back to the technical issue that the global one, this quotient is nice. You get the unframed deformation, which I'm going to use. But for the local one, I mean, it's often that this is not, so this rho bar V is not irreducible. So therefore, this frame deformation doesn't exist. Oh, excuse me. The frame deformation exists. This quotient doesn't exist. So you can't quite work with that. So that's why the quotation mark is there. So we have to reconcile these two. So this comes to the following slightly more complicated definition to make sense of this error in the box. We're going to do a little bit slightly more general. This is somehow required for later application. I will say precisely what the generality we need later on. So I want to talk about not sort of relative to all product of all local deformations. I want to take the product over some subset of the local deformations. But I want this T to I want T to contain all places dividing L or infinity. Then I define the following function. I put a frame T to mean that I want to at local places add a frame. We'll see what that means. And I want to fix determinant. Such that, maybe I'll just write A goes to the following data. So it goes to the following data. You have rho and HV, V and T. Right. Where rho, so it consists of a tuple, like so. Where rho is a lift of representations. It's continuous representation such that rho modulo maximum ideal of A is rho bar. And these HVs, they're simply just in PGL and hat A. Let me just write one last time that this is 1 plus matrix of this cross modulo 1 plus matrix cross. Okay. And later on, we're gonna the reason I introduce this notation is because I don't want to write that. Okay, it's a bit too large. Then I need to quotient out by a relation. I'll say what this equivalence relation is. Somehow I have some sort of dummy. You can think of these HVs. These are somehow dummy objects. It has nothing to do with representation. Just some elements in here, right? So you don't see them used here. We'll see how they're used later. But let me talk about the equivalence relation. So I say that maybe this is a better way to write this. So if I have a tuple like so, I say, okay, these are equivalent if I can find a x in PGLN hat A such that rho prime is conjugated. It's conjugated with, I guess, like rho prime and rho are conjugated by this x, and H prime. So this is x inverse So h prime and hv are differed precisely by this x. So in some sense, you can think of this as, if you basically ignore all the HV, this is just unframed deformation. We have these sort of dummy HVs here. Yeah, so we in this area, people work with modularity liftings. People call these HVs are some sort of dummy variables. They're not related to any Galois orientation or anything. They're just sort of matrices. And somehow this equivalence relation slightly twists the conjugation with these dummy variables. Okay. I guess roughly speaking, let me put it over here. I'm thinking how to organize the board. Let me take a risk. Sorry, let me take a look at. Okay, looks like it's possible. So let me extend the board over here a little bit. So there's another way to see it, to make it extremely dummy. It says this is also the same thing as just the usual lift. And I take h1, take one less number here of h's. Oh, this is such that gives me rho modulo maximum ideal. It's rho bar. If I take one less h here, I don't have to quotient by anything, in some sense. Right, so I can use one of them to rigidify it. In this equivalence class, maybe take the last one. In this equivalence class, there's only one way to twist things so that the last h is 1. Literally 1. So therefore, in each equivalence class, you have a precise sort of lift row and these numbers, and vice versa. And everything in the, well, I guess it's clear. So in some sense, if we really want to write this deformation ring out, so this R, so this equality has a corollary that if I really write this R rho bar framed X, or chi, excuse me, that's really sort of isomorphic to R rho bar frame, I guess completely tensor with OPGL and formal OPGL. And this thing tensor with itself, so number of T types. If you write out what this ring is, just basically there's something about the deformation ring, and there's some sort of something about the group, which is sort of, I mean, so these two are now separated things. They're not talking to each other if we write it this way. So we just have this. In other words, we can even write this as R rho bar with some sort of dummy variables, Z1, Z2. I can even remember the framed over the non-framed one has n squared minus 1 variables. Over here we have that many variables. We can all put them all together. So I have n squared minus 1 times number of elements in T, that many variables. So in the study of the modularity liftings, these sort of formal power series, these variables are not so important to us. For our later applications, we can add any framings I want to make the ring a little bit larger, but this will not affect any of sort of calculations. Oh yeah, chi, sorry. Thank you. Got the chi here. With that. Oh, chi. Sorry. I forgot the chi. Very good question. Sorry. Yeah. Of course, determinant of rho is chi. My bad. Sorry, I wrote chi and then I forgot. Other questions? Comments? So somehow this is just a variant of the usual deformation ring with some, I don't know, some not so important things. So now I want to map this to the product of another functor. The product of local deformation functor over all t. So it's a question of how to do the map. So the map uses its HVs. How the map works is the following. So I want to send a right. I don't know how to. I mean, we all know how this is defined. I'm not going to write the definition here. So, bad choice of word organizing. But anyways, let's do this one. So we have this tuple here, and I just map it to sort of restriction of representation to the local Galois at V. But the philosophy is that somehow there's no reason that the global deformation and local deformation have the same framing. In the sense that somehow the matrix representation for the global one may not somehow work to be the same matrix representation for the local one. I think there's one key reason to that, is that it's built into this theory here. So we constantly write this, this local Galois group embedded into a global Galois group, right? But when we do this, what we're doing here is that here's a local V. I'm really taking a sort of algebra. Maybe we're taking really a place of Fs above this V when we talk about this. But there are many choices of this V bar. For different choices of this V bar, this embedding is up to a conjugation. This conjugation is something you can't really control. You don't know what the conjugation is, right? So therefore, it does not make sense to say, okay, the global matrix representation will restrict to the local representation you want to deform, because you really don't know which embedding you're looking at in some sense. So therefore, you have to sort of send this, but of course, as representations, abstract representation of here restrict abstract representation of this up to conjugation. That's a well-defined map in some sense. Doesn't depend on which place you choose. So therefore, we have to sort of compensate by allowing this matrix rho and the local rho V to be differed by something. So we have this sort of factor here. And there's something to check here. I want to check this is well-defined. Namely, under this equivalence, two equivalent tuples will send to the same thing. Okay, this is a very quick check. Let's do that. So if supposedly I do HV prime, rho prime, just write rho prime V, okay? Supposedly I do this instead of rho, HV. So HV is HVX inverse. And this is X rho V, X inverse. The other one is HVX inverse, right? And of course, it should be equal. Right. Just a sec. Right. You can just check easily. So somehow on the global one, I'm really quoted by the conjugation. The conjugation is essentially on rho. But if you want the global conjugation to be sort of compatible with the local one in that sense, you have to introduce this sort of small twist on these sort of other framing variables. Whenever you get rho by x, the HV will be sort of right multiplied with this x inverse. So that's where the x inverse come from. You want to make sure that this equality holds, so you basically backsolve it, so you get this. Okay, so we have this. So this is some sort of a reconciliation of the situation, and then relating the global deformation to the local deformation. Another comment I want to say is that the way I set things up, I always require infinity, all Archimedean places to be in T. So in most literatures, this is not the case. There's no essential difference, but I personally feel like having infinity in T will make our calculations later more conceptual. That's all, just some personal opinion. So once you have a natural transformation of functors, then I get sorry. I constantly think. When I think of things, I always think of geometrically. So when I write things, I might sometimes get things wrong. I'll be confusing spec and spuff for most of the time, in the sense that we're talking about rings. Affine schemes, affine formal schemes, there's not really much difference. So the local rings, if you want to stay in the category, you have to take completed tensor. So I want to write this thing as R log. So I'm talking about a global deformation ring, global deformation relative to local deformation space, up to some sort of framing factor, which doesn't really matter. Oh, one last comment I forgot to say about here. So these formal variables, they're not important because in a lot of sort of algebra geometric sense, these formally smooth things you can make descent. So all the properties, after formally smooth things stays the same. And also if you want to check many properties, you can check it after a formally smooth extension. So that's why, so this doesn't really matter that much. So let me get rid of this. So later, let me make a remark about later application. We'll use the following two cases. Either, I guess T is just the same thing as S, or I may choose a different pair, S prime T pair, so that my S prime is S union of some auxiliary Q, a disjoint union, of course, and my T prime is still my S. So this is somehow the base case, and this will be so-called Taylor-Wells case. So later on, when we use these things, the base case will always take T to be equal to S. I take all the places. But when we play the Taylor-Wells trick, we'll start with the same S and same T and fixing T to be the same thing as S. Then I want to throw in some extra Q into the picture. And instead of considering deformations, allowing ramification only at S, I allow more ramification at some other places. But at these additional places, I don't change the local things. So I talk about the local things is still fixed to be at S in some sense. Okay. So this is how we apply it later on, but right now we're just doing the more general situation. So here's a theorem. So we talked about we talked about we talked about how this when we talk about deformation ring, we say, okay, what's the tangent space of this one is, right? And how many relations there are. And now the situation has changed. I want to look at sort of relative. I want to look at relatively this, or maybe, or in other words, so we have I'm not sure how you like geometric ones, or like if you write sort of in terms of rings, you have this ring mapping into this ring. Oh, with a chi. Do I put a chi here? Let's forget about chi. Okay. So you have the ring-wise, you have the local deformation ring mapping to the global deformation ring. I want to understand how many more variables I have to throw in here so that this will generate the global deformation ring over the local deformation ring. So originally we're looking at O goes to R row bar frame of something, right? I want to look at how many variables I have to throw in O to generate this ring. Now I want to do it relatively, so doing this relative to this one. I want to look at how many variables I have to put in here so that I generate this, and how many relations I have to quotient out by. So that's what the theorem is. So we can write a quotient of our log frame of some variables. Let me write H1. Let me just write T and R. So they're simpler. I'm hesitant. Maybe write H1 and F H2. Okay. You see where I'm getting at? Where H1 is really a dimension of H1. But now, maybe to some of you, maybe it's come to your nightmare of sort of this Silver complex, or it's a relative Galois cohomology. And H2 is the dimension of the H2 of that. Here, let's recall what this means. Recall that, or maybe it's somehow definition. I didn't quite give the definition where these two are different, so let me write this. It's a cohomology of the relative Galois cohomology. So I regret that when I talk about these definitions, I didn't really introduce the notion, the word relative Galois cohomology. This is the cone of our gamma. Of local. Okay. So that. So the we take this. This is called the relative. I mean, one should really think of this as kind of a relative Galois cohomology. In the sense, you're taking the global Galois cohomology and mapping to all the direct sum of the local Galois cohomology, and taking their cones, namely taking their kernels and co-kernels. Somehow you're philosophically you're comparing their differences. So this creates a kind of a cohomology theory, and that's somehow what this thing is. And if you take the H1 of this, that's the sort of relative tangent space of your global deformation ring relative to local deformation ring. And if you take the H2 of that, that's the relation of the global deformation ring relative to the local deformation ring. So we're gonna see that somehow the proof is almost essentially the same as the local one. In fact, I'm going to only prove it for the tangent space, and I'll leave probably an exercise for you to work on to figure out the H2 version, which is of course more complicated. So that's why I leave an exercise. but not essentially. I don't think it's essentially different in some sense. It's just a matter of tracing these notations. So let's do the proof. So I only do we only prove H1. So for H1 part. So we compute the relative tangent space. So once we know what the relative tangent space is, I would know how many variables I need to use to generate the global deformation ring over the local deformation ring. So what's the relative tangent space? So we have I'm just going to write it once, so let me write it long first. You have I always like to think of spaces, otherwise it confuses me. You have the global deformation ring, global deformation space mapping to local deformation space. So the global tangent space will map to the local tangent space, right? So I have a map from the global tangent space. R rho bar frame T chi going to the tangent, or maybe it's sort of product of all the tangent spaces of the local one. Then it will be rho bar framed chi b. Okay. So the local tangent space is a product of the local each of the sort of tangent spaces, and you have a tangent space here mapping to a tangent space here. The kernel of that is precisely how many variables you have to use to generate the global deformation ring over the local deformation ring. Think about that. Or like this, the kernel of this is how many tangent spaces for the global deformation ring that you don't see in local on a local level. So those are the number of variables you have to throw in to generate this. So that's the same thing as kernel. I mean, this, maybe I should strike. You can really prove that this is the same thing as kernel of, maybe I should say, okay. If that's not very convinced, maybe write it this way. That's going to be very messy. So because that's going to be the kernel of, oh my god, let's see, maximum ideal R rho bar. Just the notation is a bit annoying. This modulo maximum ideal R, rho bar frame chi squared bar pi. This dual, going to the product of all the pi TV, that thing dual, right? And then maybe let's dualize that everything back. So that's going to be the co-kernel. Or, I mean, it's dual, maybe I should say this is dual to the co-kernel of the local ones mapping to the global one. So that would be sort of the tensor product of the, let's see, or just sort of direct sum of all the maximal ideal of the local ones. Var pi mapping into global one. Right? And the co-kernel of this, so this is dual to this one, because I'm taking out the dual here. I'm taking the kernel of this one is dual to the co-kernel of this map, swapping two factors. And that's just, if you write down what co-kernel means, it's just basically the universal one co-kernel by the image of all the local ones. It's maybe the sum of all these v's and the universal one squared. And also var pi. And that. And that's precisely how many variables you have to generate this maximum ideal relative to the local one. Because you already put in what the local contribution could be, and this quotient by the local contributions, and then quotient by the maximum ideal of this one, and then that. So that's precisely how many generators you have to use. Okay. Anyways. That's just sort of formal nonsense. Let's come back to this way. So therefore, maybe we should start using this and then dualize. And then we get to the kernel of this tangent space mapping to this tangent space. And we know the tangent space has another way to write this. It's the kernel of deformation of rho bar framed T chi of F epsilon going to product Okay. So we want to compute this kernel. Let's see. Let's move to this board here. We need a. I like to put things in a big diagram to sort of explain things. It helps me to understand things. So let's see. So the deformation rho bar for T chi of epsilon. That's what? Remember that the way we define this is just usual deformation and some dummy things. So I can write them as Z1. Remember, the deformation will correspond to continuous one cocycles. Okay, and the dummy variables, I can identify them. I mean, they're just PGLN, right? So if I do f epsilon, so they're just essentially matrices. But I want to identify the matrix as adjoint rho bar, and there are T of them. And the conjugation will basically correspond to the quotient like so. Let me give precisely what this map is. So the lift is rho, and the lift I want to think of it as 1 plus HV epsilon. Although earlier I used HV as a whole thing, but now I want to write 1 plus HV epsilon. Right? So this lifts rho bar. I want to send it to, and for this rho, remember the way we wrote the things is that rho g is equal to 1 plus ag of epsilon times rho bar g. Right? So the rho is the lift of the rho bar to coefficient of epsilon. So the way I identify this deformation with this cocycle is to write this rho g as 1 plus something epsilon times rho bar g. And so I want to send it to the cocycle mapping g to ag. Remember that we proved that somehow whenever you have a deformation, this ag will satisfy a cocycle condition, and this part we just send it to hv. Okay, but now I have to check that on the left hand side I have equivalence given by conjugating rho and at the same time right multiplication on this one, and how that corresponds to on this side. So let's do that. So on this side, this is equivalent to the following: 1 plus x epsilon inverse rho 1 plus x epsilon. And the other one is maybe 1 plus hv epsilon times 1 plus x epsilon inverse, right? But epsilon square is 0, so this is just the same thing as 1 plus a. This is just the same thing as this. Epsilon square is 0. Now these are equivalent. So let's see what it looks like on the right-hand side. We all know that if I conjugate this by x 1 plus x epsilon, this ag is so this is something we did before. So ag is changed to ag minus x plus gxg inverse, or the adjoint action on x. Whereas hv is now changed to, sorry. In my writing, I made a trick. So suppose the conjugation should be 1 plus x epsilon, this inverse. Now I'm really conjugating the inverse of 1 plus x epsilon. So this should be no thing. So this should be h plus x. This is a trick of writing, not important. Suppose I should conjugate by 1 plus x epsilon. So this should be 1 plus x epsilon, and the inverse should be here. But now I'm conjugating the inverse of that. Same thing. But somehow maybe make my notation a little bit better. I don't know. I'm following my notes. Okay, so now it becomes plus. Doesn't really matter. So now you see what this means, how this is embedded in here. So this embedded in here through here. This is the sort of differential map. Maybe I should write partial in the group cohomology. Where over here, this is the diagonal, or sort of adding on these variables. So that's what this first term looks like. Now I want to spell out the second term. So what's the second term? I take product of all the V. We have to prove that this is the same thing as this, right? Well, I proved this. So now we have a natural map from this one down here, sending. Luckily, I have a red. Oh, I don't have a red. So let me use yellow again. So I sent this thing over here to the following representation, which is sort of 1 plus HV epsilon. I conjugate by 1 plus H epsilon, rho 1 plus HV epsilon inverse. Right? So under this map, remember that how we define comparing this deformation, this infinitesimal deformation to this one cocycle. If I conjugate my rho by that, basically this is sending to GV goes to AGV. But then I have this conjugation. The conjugation will be plus HV minus sort of GV HV. Hold on a sec. What? Right. GV HV GV inverse. The conjugation by GV. Okay. So once you have that, you see that. So this is the deformation side. I have some explicit description. So this map goes as follows. So sending the cocycle G equals to AG to this cocycle and this HV. So I'm writing down explicitly in terms of Galois cohomology of what is mapped from first deformation, infinitesimal deformation, global infinitesimal deformation to product of local infinitesimal deformation. So now, so I have some sort of explicit description in terms of sort of cocycles, Galois cocycles, I guess. So on the other hand, let's sort of get into the computation of this one. How do I compute this H1 tilde T? Well, this has two parts. Remember, there's a global Galois cohomology. There's a local Galois cohomology part. So for the global Galois cohomology part, let me write it as follows: writing the cochain complex, right? So I have this adjoint zero of this. Let me write D of continuous cochain write D? I'm a little hesitant whether I want D or partial. Should I write D or partial? I'm a little. Maybe I write D. I'll change that to D in a bit. I just worried somehow D might be misunderstood as some sort of actual letter. Okay, so I have some sort of this is a complex sorry, 2. This is a complex computing the global Galois cohomology. And we're talking about the relative thing. So for the relative one, I'm putting it over here. That's how things are defined. So this D will go to direct sum. And then this thing continues onwards. So upon the local one, it's shifted by 1 to the right. And you should look at the picture sort of vertically. So this is the first term. This is the 0th term. This is the first term. And this degree 2 term, and then so on and so forth. Look at it vertically. And there are, of course, there are maps linking these two sort of chains. So this is a restriction map. Bless you. And here's a restriction map. And here's some restriction map. And one of them has to be inverses. Shoot, I forgot which one. Sorry, I already forgot which one. One of them has to be inverses. Oh, I think I remember. This has to be the negative ones. I'll remember. Okay. Good. Luckily, I remembered. Or I could be also wrong. It could be the other one. I'm a little confused which one it is. Or maybe all of these have to be inverses again. But anyways, not important. It will not affect my computational cohomology. Okay, I have this. What do I want to compute? I want to compute, so H1. So I want to compute the cohomology at the middle piece here. I want to compute the cohomology at this place. So what kind of information I have? I have some sort of continuous cochains for the global Galois cohomology, and locally have some sort of something like that. There's some sort of matrices. Right. So let me just do some very rough calculations. So I have some. I mean, if you want to compute H1, you have to know what the co-cycle is and what the co-boundary is, right? So I have some sort of X global and some sort of XV, right? And I D of that. I mapped it over here. I want it to be 0. So let's look at X first. If I D XV, so it only goes to the bottom one. But if I do D of this X, there's some piece of this goes here, and there's some piece of this goes here. But you want this D of the whole thing to be entirely 0 over here. So that means already, so you have some X, if I have some sort of XV, which is co-cycle, at least you know that dx must be 0. When it goes over here, it must be 0. Because when it goes here, everything has to be 0. So dx must be 0, and the restriction of this x must be equal to minus of dv. Right? That's a condition for it to be a co-cycle. But for the least, I want x to be sort of after d, I have to be sort of co-cycle. So if I want to just compute the cohomology, I don't have to look at this whole thing. I can replace this gadget by just z1. Kidding me. Sorry, let me run over. So let me finish this, please. Just a couple of minutes. Okay? So I just replace by z1. Now I have this gadget direct sum with this. And I want them to have the sort of same image in here. And it takes the co-kernel. And that's and also, next thing I want to observe is that when I have something here and I restrict, or rather somehow when I have something in here, when I restrict, this is already a co-cycle. So I must restrict to a co-cycle. That's not a problem. So therefore, I can replace this by direct sum of Z1 instead of the continuous complexes. Because the image of this maps into the co-cycle of this one. If you globally co-cycle, then it must restrict to a co-cycle. Similar here, this D of this, so for D of this is contained in the co-cycle. Right? So now this looks a lot like the map we have on the right-hand side. Here, the vertical map. That's really sort of Z1 of the global one, direct sum of these sort of local places at T, and mapping it to this local direct sum of these Z1s. If I want to take cohomology on this side, I'm taking the kernel of this one, modulo the co-kernel, which is this one. So this is my H tilde 1T. And that's precisely what I computed on the kernel, on the computed kernel. I mean, this is sort of the same map as what we have on the right board. The vertical map like so. I don't have time to really write down the details and check this out. This restriction and this D is precisely the map what you have over here, but you can check it afterwards, I believe. And the kernel of this one is precisely this H1 tilde T. Okay, I'll stop here. And next time I'll make some comments about these.